Namaste. Welcome to the lecture series on the subject Basic Thermodynamics. This is Module 5, Part 1, Ideal Gases, Lecture number 1. Myself, Dr. nsatheeshkumar, Associate Professor of Mechanical Engineering, Canara Engineering College, Bantwal. So, the contents for this topic are Introduction to Ideal and Real Gases, Thermodynamics of non-reactive mixtures. Introduction. So, what is an ideal gas? So, ideal gas is a gas having no forces of intermolecular attraction. So, there is no intermolecular attraction force between the molecules. So, the gases which follow the gas laws at all ranges of pressure and temperatures are considered as the ideal gases. So, you should know what are the gas laws, and these ideal gases follow the gas laws at all temperatures and pressures. So, the ideal gas obeys the perfect gas equation PV is equal to RT and has constant specific heat capacities. The specific heat values are also constant for the ideal gas. What is real gas? So, a real gas is having forces of intermolecular attraction at very low pressure relative to the critical pressure. You see, you have to compare the pressure with respect to the critical pressure for the gas, or at a very high temperature relative to the critical temperature. So, at low pressure compared to the critical pressure, or at very high temperature compared to the critical temperature. So, real gases behave nearly same way as perfect gas. So, only at these conditions. So, they behave almost same as that of the perfect gas. So, at high pressure or at low temperature, the deviation of the real gases from the perfect gas relation is appreciable. So, usually there will be some error. That means it is not the exact that of the perfect gases. So, due to this reason, so many equations have been developed for real gases, the derivations of which may be analytical based on the kinetic theory of gases, or some equations of state may be empirical relations derived from the experimental data. So, why these equations of state have been derived? That is to overcome the deviation from the property values of the real gases at high pressure and at low temperature. So, we know that here is a mixture of oxygen, nitrogen and other gases. So, the thermodynamic behavior of gas mixtures depend on individual properties of constant gases. So, whenever you study the mixture property, so you should know the individual properties of the constant gases. So, the constant gases do not interact with one another chemically and are assumed to be ideal. So, each of these constant gases which makes the mixture are assumed to be ideal, and they also behave independently. So, a non-reacting gas mixture can be treated as a pure substance since it is usually homogeneous mixture of different gases. So, a substance which is homogeneous in its nature, so it is called as a pure substance. So, a non-reacting gas is also treated as a pure substance. The properties of a gas mixture obviously depend upon these properties of the individual gases. So, usually these gases are called as the components or the constants. So, it not only depends upon the properties, it also depends on the amount of each gas in the mixture. The percentage composition also affects. Therefore, it is possible to prepare tables of properties for mixtures. So, this has been done for common mixtures such as air, because even you know that air is also a mixture of gases. So, such property tables have been prepared for that. So, it is not practical to prepare property tables for every conceivable mixture composition. However, since the number of possible composition is endless, so even though it is the composition is limited, so it is not practical to prepare property tables for every mixture. So, therefore, it is better always to develop rules for determining mixture properties from a knowledge of mixture composition. So, better you develop some empirical relationships so as to find these mixture properties from knowing the properties of the mixture composition. The properties of the individual components also. Okay. The basic principles involved are applicable to liquid or solid mixtures called solutions. So whatever the principle applied to develop such rules is also applicable to liquid as well as solid mixtures. Now coming to the thermodynamics of non-reactive mixtures. So here it is based on the few assumptions. So what are the assumptions? So each individual constant of the mixture behaves like a perfect gas. The mixture behaves like a perfect gas. Individual constants do not react chemically when the mixture is undergoing a process. You see, look at these three assumptions. Each individual constant of the mixture behaves as a perfect gas. The mixture also behaves as a perfect gas, and there is no chemical reaction. The individual constants do not undergo any chemical reaction. Okay. Now mixture characteristics. Consider a mixture of gases A, B, C. You can see inside a container there are three gases A, B, C existing in equilibrium at pressure P, temperature T, and it is occupying a volume V. You can see here. Okay. The total mass of the mixture is equal to the sum of the mass of the individual masses. So m. So m, here suffix m indicates the mixture, and this m indicates the mass. Similarly here this m indicates the mass, suffix A, B, C, so they indicate the individual gases. So total mass of the mixture is equal to the sum of the masses of the individual constant elements. Okay, individual constants rather. Okay. Now mass fraction. The mass fraction of any component is defined as the ratio of the mass of that component to the total mass of the mixture. So it is denoted by mf. So suppose if you have three components A, B, C, so mass fraction of component A is nothing but mass of A divided by total mass of the mixture. What is the total mass of the mixture? That is nothing but Ma plus Mb plus Mc. So similarly you can write expressions for Mfb as well as Mfc. Now you should know that the sum of mass fractions of all the components is always equal to 1, because it is based on the total mass, so it will be always equal to 1, where the subscript I stands for the ith component. It shows that the sum of this mass fraction of all components in the mixture is unity. Okay. Coming to the mole fraction, if the analysis of the gas mixture is made on the basis of number of moles of each component present, so it is termed as molar analysis. So here total number of moles of the mixture is equal to the sum of the number of moles of the individual gases. So it is identical to the mass. So here total number of moles m suffix m is for mixture is equal to the number of moles of A plus number of moles of B plus number of moles of C. So what is a mole of a substance? So a mole of a substance has a mass numerically equal to the molecular weight of the substance. So 1 mole of the substance is always weighing equal, mass is equal to the molecular weight of the substance. For example, 1 kg of O2 is having 32 kg, because O2, O is 16, 16 into 2 is 32, whereas 1 kg mole of N2 has a mass of 28 kg, because N is 14, 14 into 2 is 28 kg. The mole fraction of any component is defined as the ratio of the number of moles of that component to the total number of moles. So it is denoted by Y. So Ya is equal to number of moles of A divided by total number of moles in the mixture. Similarly, you have the expressions for Yb and Yc. And also you should know that the sum of these mole fraction also makes up to 1. That is the sum of the mole fraction of all components in a mixture is unity. The mass of a substance m is equal to the product of the number of moles n and the molecular weight. Okay, this is very important relationship. Suppose if you want to find out the total mass of any substance, and then you have to multiply the number of moles of that substance with the molecular weight of the substance. So therefore, for each of the components we can write Nm, that is the mass of the mixture, Nm into mm, that is the mass of the mixture. Here this is the number of moles of the mixture, and this is the molecular weight of the mixture. This is very important. This is the molecular weight of the mixture. So it is equal to, this is the mass of the mixture, right? So it is equal to mass of A plus mass of B plus mass of C. But what is mass of A? It is Na into Ma. Whereas mass of B is Nb into Mb, and Nc is Nc, mass of C is equal to Nc into Mc. So where mm is the average molar mass or molecular weight of the mixture. So this mm is called as average molar mass, or it is also called as the molecular weight of the mixture. So you can write the molecular weight of the mixture as mm is equal to Ya into Ma plus Yb into Mb plus Yc into Mc. Now why did from where did you get Ya or Y term, which is nothing but the mole fraction. You see, if you bring this Nm to the other side, so here it becomes Na by Nm, that is the number of moles of A divided by total number of moles of the mixture. Similarly, Nb by Nm, Nc by Nm. So Na by Nm is nothing but Ya, mole fraction of constant A. Similarly, mole fraction of constant B and mole fraction of constant C. So thus the average molar weight of a gas mixture is the sum of the products of all the components of the mole fraction and corresponding molecular weight of each component. Now this is just the introduction and a few basics about the ideal gases. With this I conclude, because I want to keep the lectures very short, so that you can spend little time in watching each of these individual videos. So I conclude this lecture number 1 and will continue with lecture number 2 for the same module in the next lecture. Thank you.